And again, welcome back, everybody. I'm glad you're here. This is part 10 of my YouTube series about a heavy lift drone. We are looking at Start Point Lighthouse in South Devon, England. In part 10 of these YouTube videos, I'm going to talk a little bit about what I call the law of electric motors, which addresses whether a heavy lift drone is required to have electric motors turning the propellers. I'm not sure that's true. And I'm going to go and we're going to fly ourselves out to Gunnison in Colorado, and I'll talk a little bit about why I think, particularly initially when heavy lift drones are created that carry human beings, I think they need to have flying ability with wings, fixed wing flying, because that can act to save the human beings if there's a catastrophic loss of power. But that's the second part. I do have a YouTube channel. The name of the channel is Patrick Gray, and I invite you to become a subscriber to the channel. I think you will enjoy it. And as we have mentioned, we are going through a Corel Draw graphic document on this topic of the setting up controlled modulation and adequate power for a heavy lift drone, and we'll take a look at that document. And here is the Corel Draw document that we're looking at. We've done a lot of these pages. And there are a few pages. This is the section that we're doing now. This has to do with the law of electric motors and how drones are controlled. And I will go back to this page and once again bring out the concept that it's a disclaimer, any physically real object has the potential to be dangerous, to hurt people or damage equipment. The people who create a physically real object should create it and manage it in a manner that is legally allowed and reasonable and safe. And my advice is, do not create a physically real item if you cannot manage it in a manner that is legally allowed and reasonable and safe. So this is a YouTube discussion, and we're just talking. And don't make any of this stuff if you're not able to properly do that. And this Corel Draw document is available. I'll show you where you can go to my website and download the document. We are going to eventually we're going to start doing, demonstrating some calculations. And I don't want you to feel like you have to follow along and write stuff down. So you can download this document and you'll have the calculations. And here's how you get to it. And so here's my website. I do talk about robots, but there's another area where I don't talk about robots, and so you can click on that. And this is a little guy that just watches over my website. Here is the heavy lift drone right here, that topic. And you can go down into this heavy lift drone page and click right here. If you click on this, it will download a 60 megabyte PDF file that has all these pages in it of this Corel Draw document that we're talking about. And we'll move on now to the part 10 YouTube video. There was a few other sort of catch-up things I wanted to talk to you about before we get to the numbers for the drone. I have been talking about this CTS 800 engine. The LHTEC was a company that got together with a partnership between Honeywell and Rolls-Royce to make this CTS 800 engine. And these specifications are out there. This is a dimensional drawing and showing some RPM and Newton meters and power outputs. That's all on the internet. And this is the European Aviation Safety Agency, where they take these, this is the LHTEC, Light Helicopter Turbine Engine Company, CTS 800. These are specifications that are governmental documents, so it's unlikely that these are not true. And there's a whole bunch of them, but you can get from them specific things that you need to have if you're going to design a drone, like weight, size, power outputs, Newton meters, RPMs. Okay. These are things that you need to know in order to design a drone that's a reasonable drone. And the other thing that I wanted you to see was I went into my SketchUp program and took the Parker Hannifin F12 pump motors and made a little drawing and laid it up against their actual drawings. And these are all to scale. And this is, here is the listing of all of these different pump motors with how big they are, what their maximum pressure is, what their operating speed is, motor flow, weight. So you can put together your opinion of what you're going to do so this thing will fly, and then you can go and look it up here. And if you're not inside of these values that they have, then you have not created a design that's reasonable. So that's very helpful. And the other thing on page 8 was the law of electric motors, and I'm going to get into that with a higher quality version of these images. And we need to talk about what was it that allowed drones to work. It was something they discovered that was a bit of a surprise. First of all, they needed a very high quality tilt sensor that picks up how much the drone has tilted in all of its axes. Not only does it have to be very accurate, but it has to redo its values very rapidly, like 10 times per second. That had to be invented, and they finally figured out how to do that. Then they discovered they can send tilt information to a central processing calculating device, and that calculating device can figure out what should the motors be doing to take care of the tilt that's present, because any physically real structure, there's just going to be variabilities of the air and the wind currents and the air coming down off of the propellers and bouncing off of the ground. It's all going to keep changing. So this drone is going to constantly be shifting. It's going to want to go this way, then it's want to go that way, then it's want to go this way, it's going to go up, it's want to go down. It's what it's going to do. And you might as well know that and do something to respond to it. So if it starts tilting to the right, you need to add power over here to push this wing back up and take power off of here to let this wing come down. And the exact moment you do that, now it's going to be tilted to the left. So you have to put power on this wing to push it up some and take power from that wing to bring it down some. And that needs to be done in a loop where the sensor picks up what's wrong, the CPU thinks about it. This is the big source of power. It's got a lot of power in it. The big heavy power is not allowed to go directly to the motor. The big heavy power goes to a modulation structure that decides how much power it wants to send to each of these 6 motors. And this modulation device takes its orders from the central processing unit. So the central processing unit says, here are your 6 propellers, here's how much power I want them to have. It takes that power from here, it sends it to those 6 propellers. The tilt sensor reassesses what happens, sends its result to the CPU. The CPU says, okay, well, I did this and it had that effect, so this time I'm going to do that. And this loop goes around like this. And this loop goes around 10, 20, 30 times a second. And what they discovered is human beings cannot do this. It's too much. The calculations are too complicated and they have to occur too rapidly. They need to have a system where the interaction of tilt, processing, modulation, effect can happen really, really fast. And what they realized and figured out, what they been true for a long time, is that electric motors can rapidly alter their RPM values. And you can change it from 1,000 RPM to 984 RPM, and then change it from 984 RPM to 1,007 RPM in a millisecond. Electric motors can do that. Thus, they put electric motors in the drones. All right, and you can see we have mentioned this loop of drone control here, where the CPU, the central processing unit, is keeping the drone stable by altering the thrust output of the propellers in an ongoing and continuous fashion, so that whatever abnormality was picked up by the tilt sensor, this is probably cycling 10 times a second. So whatever abnormality was picked up by the tilt sensor got down to the central processing unit, and it decided what it wanted to do about it. And you can see that all of this stuff over here I'm not talking about yet. This is just this loop that goes around and around and around, and that will the central processing unit, through its ability to alter this modulation device. This modulation device controls how much power goes to each motor. And remember, the power that's going to each motor, a tenth of a second later, a different amount of power might be going to that motor, depending upon what happens with the tilt of the drone. And an issue that occurs is, as the drone begins to tilt, the longer you wait to, or let me rephrase that, the longer the central processing unit waits to do something about that tilt that isn't wanted, the more the drone begins to be out of control. Because when the drone tilts, if you have it in a stable hover where it's just hovering, not going forward, not going backward, not going left, not going right, not turning, not going up, not going down, it's just hovering, the vertical thrust output of the rotors is equal to the weight of the drone, and it's directed straight down. But as the drone begins to tilt, some of the vertical thrust is converted into a component of horizontal thrust. So if the, let's see here, the right wing of the drone tilts down, two things happen. First of all, you don't no longer have enough vertical thrust to hold the drone up. So as soon as the drone tilts, it will start losing altitude. The other thing is, some of the vertical thrust now has a component of horizontal thrust. So when the right wing tilts down, the drone will start moving to the right. So it will move to the right and it will move down. And the longer you wait to work on this, the more difficult it is to fix it. So you want to have that effect quick. And this is why that, plus the fact that human beings can't control a drone, is the reason why they went to electric motors, because electric motors can change, let me rephrase that. if you take a digital power modulation device and request that an electric motor change its RPM quickly, an electric motor has the ability to do that. So instead of giant compensation effects over longer periods of time, what you can do is have little tiny, very rapid, immediate changes of the motors to get the thrust to be what it's supposed to be, so that the amount to which the drone is off is not as much. And so your compensation doesn't have to be as much, and it tends to stay where you wanted it to stay. And electric motors can do this. Another thing that we need to discuss is what happens when you add human beings into this situation. And one way to add human beings is to create this device. This is a box, has 6 dials on it. Each of these dials is directly connected to this motor. And what happens is this is a wireless connection between this box and the modulator. So this is not in it. This is not in it. The sensor is not in it. All of this is not in it. That's not in it. None of this is in there. This box talks to this. Whatever you do with, say, this dial, let's pick this dial. This dial right here controls that propeller right there. Whatever you dial in on this dial, that's the RPM that this propeller will have. And whatever you dial in with this dial is the RPM that this propeller will have. And if you handed that box to this little person sitting here and said, go for it, and you turned off the central processing unit and the tilt sensor, and this person, this lady or this guy is just looking at the drone, and you said, all right, do it, man, get it going, it will immediately crash. Because what they discovered is human beings simply cannot do the calculations fast enough to decide what to do with these dials. Not only that, they can't move the dials precisely enough to have the exact effect that's needed. And the last part of it is they don't, with their hands, can't move all 6 dials at the same time. So the very moment you give independent, autonomous authority control of the rotors of a drone to a human being, it will immediately crash. And so what they discovered was you set up a computer system where the human being is saying to an interface, this is what I would like. And the interface takes human being keyboard, joystick, mouse commands, maybe voice, probably more joystick and keyboard commands. That interface turns it into digital information that the CPU can deal with in a digital fashion. And the CPU says, basically, okay, thank you. I appreciate that you told me what you would like this drone to do. And the CPU then says, I, the CPU, will work what you're requesting into the work that I'm doing to keep this drone stable. So the CPU is running 2 processes. One process is keeping the drone stable, and the other process is trying to take what the human being asked for and insert it into the commands, so that if he said go up in the air 8 feet and then continue your stable hover, the CPU will work that in there. But to the human being, he or she might have the feeling, I'm in control of this drone, but they're not, and they can't be. What they're not, all they have control of is the CPU has been told that it needs to adjust its algorithm so that whatever the human being is requesting, the CPU needs to go ahead and try to get that to happen. And again, you'll notice that this part of this loop is unchanged from the part of the loop that existed when there was no human being involved. This is why it's so easy to do autonomous flying with drones because they're already doing it. All the human being is doing is telling the drone what it would like for the drone to do. And that's a very important concept to understand. It's a little surprising, but it's true. And this use of electric motors to do this had an interesting effect that it caused. And we're going to talk about that in a second here. All right, and before we go on more about the drone and how it's going to get up into the air, I want to tell two stories, or one story and a discussion. There was a science fiction writer, Isaac Asimov. This is from Wikipedia. He received a PhD in chemistry and was a teacher and professor, but he was a writer and a science fiction writer and wrote a lot of things on a lot of topics. He wrote Foundation about what would happen to a civilization if things were not going the right way. And he also wrote a series about robots. He put in his robot stories the concept of, to ensure the loyalty of the robots, there were the 3 laws of robotics, which he wrote down. And we see here again in Wikipedia that Asimov thought that his most enduring contributions would be the 3 laws of robotics. And they are a discussion of what robots are allowed to do and not allowed to do. And it's built into their programming. And for many years, for a long time, a lot of people did not know that this laws of robotics were something that Isaac Asimov, a writer, just wrote down. These laws were not created by a legislative body anywhere. And can just show you that writings and words and phrases can become, quote, laws when they're applied as being laws that have to be, when they actually are just what someone thought or what a group of people thought. It isn't actually been established as fundamentally true or a law of the universe. And we will leave Isaac Asimov, a science fiction writer and a science writer, and go to a story that I just created. And this story involves a person who is scientific and has a technical job and spends his time doing scientific technical work. And he has a brother. The brother endorses the simple and unencumbered lifestyle and lives out in the country in his farmhouse that he tries to run without much connection to modern technological society. But he does have to obtain some income and food for his family, so he has some land that he plows. And his brother, the science technical person, comes to visit him. And of course, the plowing is enough work that the countryside brother was happy to talk to his technical brother, but it's like, you need to come on outside with me while I'm doing this work. And so the brother puts on, out in the field, a harness around his waist and stomach, and then hooks it to a plow and begins pulling the plow across the land to create a furrow. And while he's doing that, his more technological brother notices the fence and the grassy field, and in that field are 4 or 5 horses. And he says, I'm seeing those horses over there. What is that all about? And his working brother, the brother that's pulling the plow himself, says, oh, well, those horses, they're our pets. We have them. And his technological brother says, well, what do you do with those horses? And his outdoor, simple life brother says, well, we just feed them. They have 6 or 7 acres out there they run around in. We'll look at them. Sometimes we go in there. We can ride them. It's not that hard to do. And he's pulling along, creating a furrow in the ground. And his technological brother says to him, you know, you can make a harness and attach it to one of those horses, and they will pull the plow, and they will pull a lot more of a plow than you can pull. They will make a deeper furrow so you have better yields and can get different types of crops, and they will plow it so much faster that you can plow a lot more land than can be done by you, and you'll have more to sell and more for your family. And his out in the country brother just stops and looks at him and says, what are you saying exactly? And he says, you don't have to pull that plow. The horses can do it. There they are. They're right on the other side of that fence. The only thing you have to do to use those horses is hook them up to a harness. And his more outside in the country brother says, well, you know, I'm going to have to think about that. And the clear, I think, and obvious point I'm making here is the bent axis hydraulic pump and bent axis hydraulic motor, they already exist. They have been created. They're a product for sale. If you want one, you just purchase it. You don't have to have anybody create a 180 horsepower electric motor that is certifiable for aviation use. And you don't have to have somebody figure out how to make a battery that could power 6 180 horsepower motors for more than 10 minutes. And there's nobody 8 to 9 to 12 years old digging in a cobalt mine somewhere to create a bent axis motor. And the bent axis motors have a axial radial stabilized roller thrust bearing in them. They already are in use running propellers. I don't know if they've been certified for aviation use to lift human beings up in the air, but they exist. And they're just there. It's exactly like having those horses over in the pasture. If you wanted a bent axis hydraulic pump and motor, you just simply have to acquire one. They're available and for sale. So it's just a point I wanted to make. All right, and we are finished with the story about the brother and the horses. And what I want to do now is go back to talk a little bit more about the Isaac Asimov effect, where a quote law was just created out of nothing. And it took a long time, it took a long time for people to realize these were not laws. These laws got incorporated into other science fiction stories. And again, it took a while for people to realize these were not laws that had been created by any legislative body that had the legal authority to create a law. This was something that Isaac Asimov just made up. Okay, and it had this status of laws. And the reason I'm talking about this is it hasn't been written down, but there's a sort of almost a law related to drones and electric motors. The hypothesis that I am making here is that the motor of a drone does not have to be electric. It can be electric, but it doesn't have to be electric. It can be mechanical. I do agree that if the drones are small, if the drone is the size of a baseball or the size of a basketball, it's going to be difficult to get that level of control of a motor, of a device spinning a propeller other than electric. But we're not talking about that. We're talking about heavy lift drones. We're talking about drones where each one of these propellers is creating 933 pounds of vertical thrust. This is a lot of power. It's a big motor with a lot of power. And electric motors maybe can do this. Mechanical motors can, because they already do it all the time. These motors that can do that already exist. And this is where I want to talk about this concept of a law or a rule of drone action that just simply occurred. And the effect that it led to was what I call the law of electric motors. Now, what it is that electric motors are required to turn the propellers of drones. That's the law of electric motors, because it's always been that way. And the reason this is true is because, well, it's just a feature of the universe, and that is that. Or, well, it would violate one or more fundamental laws of physics if they used a motor that wasn't electric. Or, a successful non-electric solution would require a very special type of genius that shows up in intervals of 200 or 300 years, like Michelangelo or Einstein or Newton. And that genius on the topic of drones isn't here yet. Or the successful non-electric solution would require collaboration of university, government, and military, multiple PhDs, long amounts of time, and a whole lot of money. And none of this is currently available. Or a successful non-electric solution will require a very special, sophisticated, and complex piece of equipment, really hard to understand and make, and nobody has been able to figure out how to make this yet. Or, on the very specific topic of the hydraulic motor for propelling the propellers around, that's going to require a very special valve to modulate the thrust so that you can get the RPM changing like it was changing with the electric motors. And that very special valve is going to have to be very reliable, very robust, very precise. It's going to be able to cycle hundreds of times per minute, and it has to be a digital interface between the valve and the CPU, because human beings can't be involved in it. And the truth is, there's not anyone anywhere that has any idea how to do and create a valve like this. And of course, my opinion is every one of these is just not true. The universe does not care what turns a propeller. The laws of physics, you got the energy, you get something spinning around, it'll turn a propeller. None of these solutions require any particular clever thinking. They just need to have people who believe in it and can work on it. The military and the government, they're all tied up with electric. Fine, I don't mind them doing electric. We'll go back to those soldiers laying there being shot at and facing certain destruction and injury and death. And the question would be, do you think any of those soldiers would call that commanding officer and say, well, I know you have this drone that's going to save us, and it's in the air and everything, but could we have one question for you. Is that drone electric, or does it run on fuel? Because, if it's running on fuel, it's okay. You can bring it back. We don't want it. We don't want to be saved by a drone that runs on fossil fuel. You think any of those soldiers are going to say that where they're laying there face up against those rocks while people are shooting at them? Do you think any of those soldiers are going to say, hey, look, we got cell phones. Would you text us a picture of the drone? It's not really that pretty. It's okay. We don't want to be saved. I mean, what does it look? What color is that drone anyway? You think any of those soldiers are going to do that? So if somebody wants to make a beautiful drone and have the young lady and her precious children fly downtown so they don't have to ride in a taxi, I don't mind. That's fine. Go for it. Build that. I would like to save those soldiers. And so for some reason, non-electric solutions are just not a big issue. But you know what? I think if you make a drone that can lift 1,600 pounds and fly off with it, you'll sell as many of those as you want to sell. And so I think it can be financed at the industrial level, because I'm trying to show you here, putting together how this works is not that difficult, and it's not that expensive, and it can be incrementally constructed where you don't have to do the big expensive step until the little inexpensive step is shown to work. And I'm showing this to you step by step. I don't think it's a special complex part, and I think this valve can be created. I will show you how to make this valve. I have a design for it that I think will work just fine. Here is the design that I'm talking about. Now, this is the Allison Rolls-Royce. It's the Rolls-Royce owns it. It's the Allison 250-C40 turboshaft jet engine. Here's the turboshaft spinning the gears, running the 3 pumps. I'm just showing one pump right here. Pressurized fluid comes out of the pump. This is a manifold. I have this sticking in there, but this is big because all 3 pumps are feeding to it, but it'll be all sealed up. So the fluid comes out, it goes into this manifold, comes up here, and this brass valve is here, and it flows past that valve, and it goes up this pipe to that motor. That motor spins this propeller around, and the return flow comes down through this pipe, goes back through here, and goes back to the pump. And you can see by moving this up and down, this has a hole that goes from here to there. So there's no net pressure differential between here and here. That's not how this valve works. This stem comes down and occludes this space right here. And remember, in a drone, you're never going to stop the flow. All you're going to do is modulate it. You're never going to take the RPM to 0. It's going to go from 2,425 down to 2,421. And then it's going to go from 2,421 to 2,429. So all you're doing is moving this up and down and interfering with this flow. I tried to make a shape that doesn't generate a lot of turbulence. And this goes up and down, and the low pressure side is separated from the high pressure side by this seal that is a standard traditional high pressure packing type seal. And what is making this happen is this structure. And this structure is a ball shaft, ball nut system. Inside of this geared structure is the ball nut. And so what I did is, in most of the time with ball shaft, ball nut systems, they spin the shaft around and keep the nut still. Or at least they keep the nut so it can't turn. So when you spin the shaft and the nut can't turn, then the nut moves. And the moving part is connected to the nut. But that has an asymmetrical thrust to it. And I didn't like it. I don't think it's a good way to do this. And so what I did, this structure has rollers on it that roll on these right angle beams. And so this structure cannot turn. It can go up and down, but it can't turn. And since it can't turn and it's clamped to the ball shaft, this servo motor is geared down through these gears and spinning the ball nut that's in here. And these two structures here and here are radial axial stabilized thrust bearings. So that ball nut that's in there, it can't go this way and it can't go that way. All it can do is spin around. And when that ball nut spins around this ball shaft, it moves the ball shaft up and down. And the accuracy of axial motion on the ball nut ball shaft systems is in the level of 3 to 5 microns. So you can move this structure at whatever level of accuracy you want. And the ball shaft ball nut system, in terms of running forwards and running backwards and running all the time and being adjusted hundreds of thousands of times per minute, They do that all the time, all over the world for years and years and years. All of this already exists. You can go and buy all these parts. I think this structure is so simple, I don't think you could patent this. You can make your own and nobody's going to take it from you. And this, okay, you can see I have a manifold here, okay? So there's 6 of these. 6, what is this? We got the top is the return and the bottom is the pressure. So there's 6 pressures and 6 returns. And each one of these runs one of these motors on these 6 propellers. And there's 6 of these linear actuators. 1, 2, 3. So there'd be one of these here, one of these there. And each one of these has a digital interface. And the companies that make the servo motors make the digital interface. It's a part of it that they'll sell with it. And they make these servo motors with brakes on them. And they have program code that they will sell you for free, telling you how to speed up the motor, how to slow down the motor, how to make it go forward, how to make it go backwards. All of that already exists. So you have a digital control of RPM that's just as good as the digital control of electric RPM. Except with electric, you can get to 40 or 50 horsepower. With hydraulic, this can go up to 190 horsepower. And you can put 2 700 horsepower jet engines in there and have a 1,500 horsepower drone that can carry real capability around, real significant payloads, like 12 of those 40-pound smart mortars and 2 people, and it can fly for 3 or 4 hours. Electric just cannot do that. And so this is my solution, or my proposed solution, and I think a good machine shop could make this for you in 4 or 5 weeks. There's nothing to it. And the nice thing about it is, just make one of these. Yeah, all of the stuff that I design, I try to design it from a scale viewpoint where there is no inherent scale to it. You can make it bigger or you can make it smaller. Nothing about the way it works is altered by changing if it's bigger or smaller. It just changes how much fluid can flow through it. That's all it changes. And so that's my suggestion of what we can do to get these propellers controlled in a hydraulic manner. All right, and I think that finally we're now at a place where I can talk about numerical calculations. We're looking here at Emerald Lake and the South Klondike Highway. I wanted to make the argument, I think, it's one thing to have drones. Drones exist. They're not really new technology anymore. But drones that carry human beings are new technology. And they fundamentally don't exist yet. Now, I was in the caring professions for a long, long time. I know if I was creating a drone and had money, people were giving me funds to create a drone, I think 95% of my concern would be to establish a stable hover. I think with a drone, if you have a stable hover, you've solved most of your problems. And what's left is just making it pretty or adding features. But if you have a stable hover, you have a drone. And if you don't have a stable hover, you don't. So 95% of my work would be establishing, maintaining, and being able to get into and get out of a stable hover. What's interesting, if they needed me to go and work on a drone that was carrying human beings, what would happen is 95% of my time and concern and attention would be making sure that that human being was safe. And the complete entirety of the rest of the work about the drone, all that used to be everything I was thinking about, that would be compressed into 5% of my concern. 95% of my concern would be not allowing someone to get hurt. And I want to make the argument that the device that should be given this classification of drone when it comes to human beings, I think it should be done with an airplane that already exists, that already can fly, that pilots are familiar with. Planes with no power, it's a problem and you're in trouble, but at least you can try to glide it down and land it. If you're in a drone with no power, you're just headed for the ground unless they come up with parachute systems, which is not quite there yet. And remember, you can be 12 feet off the ground and fall 12 feet. That's a serious impact. And there's very few parachute systems that are going to work to protect you against a 12-foot fall. So that's why I wanted to suggest the concept of using a plane. An interesting thing about an airplane, if it's old or it hasn't been maintained properly, or for cost reasons they didn't want to do the required maintenance, the plane loses its certification for use as a device to carry human beings, which means its price goes way down because it's not really valuable. You can obtain this plane and put the VTOL drone equipment on it and use that for your team to figure out how to get a stable hover in this plane using a piece of equipment that already exists and already can fly. And this leads us to the first set of pictures that I created. And I spend my time flying around Gunnison River, the black Gunnison Valley. Some of it is a national park, some of it is land in Colorado. And I thought, I'll just put the drone right there. It's an interesting story about pilots. I was in the Navy. Everybody said, pilots, they're careful, they're meticulous, they pay attention, they've got some degree of engineering skill and thinking. They understand their plane and take care of it. They know what it can do and what it can't, and they are able to calculate what they're supposed to do in order to keep themselves properly aloft and stable. But the other thing that was in the military was, at least to the people I was dealing with, not in an unflattering way or a mean way, it just was everybody understood pilots are crazy. They do stuff that regular people won't do. And this is a plane, this is 1,500 horsepower. This is a plane with 5,700 pounds of thrust in a plane that weighs 5,700 pounds. This is almost a rocket ship. And and I know, if a pilot got into this thing and had permission, would they land it right on the edge of this valley? Yes, they would. And if they could get permission from their handlers, would they fly this thing down in here and land it on the edge of the river? Yes, they would. And this, now, you got to get into Google Earth. This is fairly flat. I don't think a pilot would land this on a slope like this. But I'll see if I can get to this place again. It's pretty flat here. And I did a different view. The conservative, caring profession person kicked in. And maybe a little bit more conservative pilot would have landed the plane over here. But you can fly right up to here, put it in drone mode, and put it right in the ground. Just land it. There it is. And, what what pilot would not do this? I think they would. The other one, this is a valley. I'm going to talk to you about this valley. But in my opinion, absolutely, these pilots would get in this plane. Now, the plane is sitting with its tail down and its nose up because its wheels are on the ground and its little back wheel is on the ground. So it's sort of pointing up. And when it gets ready to take off, it would get itself level. So don't be worried that it's pointing up in the air like that. But would a pilot put that plane? This is, again, we'll go on Google Earth and show it. This is flat. Would they land this thing here and look out over this valley? In my opinion, yes, they would. As soon as they could somehow get permission to do it, they would take this conservative, safe, and flying that they're doing in the valley, and they'd bop this thing right up over the edge of this ridge and turn it around and land it right there. That's what they would do. All right, and so we'll go do a couple other things real quick, and then we'll talk about flying. And I will say that flying in Google Earth Pro is counterintuitive to me. So sometimes I get myself mixed up. This is Colorado, somewhere on right there. That's Denver, and we're going to Montrose Regional Airport, which is 167 miles from Denver. Remembering that we could fly that drone to Denver and get it up over these mountains and back down again in an hour and a half worth of flying. And it looks like Montrose has a 10,000 foot runway. I can't imagine why it does, but it does. And again, if it was me, I wouldn't want my people not to get hurt. So I would get permission and I would have the military execute a contract with Montrose Regional Airport where you would power up the drone with drone flying and go up in the air 4 or 5 feet and then go down this runway until you had enough airspeed that you could just fly off. And if anything went wrong and you had a catastrophic loss of power, you're 5 feet off the runway, you just land it. I would want to, the DHC, de Havilland, has wires and pulleys running its flight control surfaces. I would want to put one of those linear actuators. It can develop 300 or 400 pounds of force on those wires and pulleys. You would need one linear actuator for roll and one linear actuator for pitch, one linear actuator for yaw, and one linear actuator to put down the flaps so that the CPU could fly the plane. I would do that. And I don't know how complex it is, particularly if you're the military and it's not a commercial plane but an experimental plane, to add fly-by-wire to a plane that already exists. But I would want the CPU to be in charge of the plane. And I would tell my guys, somewhere, what was that? Oh, it's gone now. The Black Dog Equipment. Somewhere down in here in metropolitan Montrose, I would rent a couple of condos and get some of those buses that the musicians tour in and plan to be here for a year. And I would take that drone every day and have them run down the runway and put it up in the air, go out over here where it's flat, where they can land if they need to. I would want them to get on up in the air when they could, because the higher they are in the air, they have the ability to glide to a landing if they had a catastrophic loss of power. But they could go down the runway 3 or 4. There actually what they would have is a runway made of air, because they would be flying, fixed wing flying, like they were on a runway. They just would be 2 or 3 feet in the air. And I would have them go up here and fly around and come back and bring it down over the runway and then land it and then take off and do that again. Now, that's one thing. We got to look at flying the plane as a drone and also flying it as an airplane. And so, again, I'm trying to navigate flying with Google Earth. I laid out my maps here, and this I think is 14 miles. But you fly out over these fields, because what we would like to do with the drone, and then you come up to Highway 50. The guys could leave their animals at Pearl's Pet Lodge if they needed to. Unless they had cats, then they could leave the cats there. And I would have them follow up this road. This is all flat land, so they could land if they had to. If they had a catastrophic loss of power, they'd just convert it to an airplane and do a gliding landing. And we would take the buses, or the tour bus type bus, and we'd have a tanker full of fuel and a couple of tour buses and a telemetry system and some scientific data material. We would want to talk to the Flying M Ranch, and I have to say I'm worried about the Flying M Ranch because they made it pretty clear what they think. But maybe if it was a governmental contract, and we would put the plane right here. So they would fly at 135 miles an hour, 120 miles an hour from the airport. And that distance is uh, 9 miles. So they would get there, and it would take us in the buses to get there 30 minutes, and they'd be there flying around in circles waiting for us. And what I wanted to do was to have a course to fly, and I'm going to say flying in. And I guess before we do a lot more flying, we'll do a very quick math analysis. This again is a CorelDRAW graphic presentation. The drone is new, so the flight testing would be conservative, worrying about sudden loss of power. So we'll go down the runway with excess vertical thrust converted to horizontal thrust by altering the tilt of the rotors. We will use the VTOL to get the drone to go straight up in the air 4 or 5 feet. The 5,700 pound drone has 39 pounds of thrust, so there's 239 pounds of thrust left over, which can be converted to horizontal thrust to give an available horizontal acceleration of 1.35 feet per second. We get this horizontal airspeed of 60 miles per hour, then the lift created by the wings is equal to the weight of the drone. So if you have a sudden loss of power, you can just land it. And the acceleration calculation shows us going from 0 miles per hour to 60 miles per hour at 1.35 feet per second squared will take 2,870 feet going down the runway, 4 or 5 feet off the runway, and take 65.2 seconds to do that. At that point, the plane is being supported by its wings, and you can turn off the back 4 rotors and turn a little more power to the front 2 rotors and bring it up to 125 miles an hour flying time, or flying speed. And the flight that we're talking about is a flight, this is the initial safe testing from the Gunnison Regional Airport, Montrose Regional Airport in the Gunnison area. A total of, I think it's 10.9 miles to a location just north of the Flying M Ranch. That is done under fixed wing flying at 125 miles an hour. 10 miles will take 5 minutes. And then we will do our testing of the drone flying in this little piece of it, which is 3.2 miles. And that gives us this set of calculations. Montrose Regional Airport, altitude 5,711 feet, 10.9 miles, to start our ascent. At 7,244 feet, we will ascend to 8,690 feet over a distance of 3.2 miles. 11 miles at 125 miles an hour is 14 pounds of fuel, because it burns 136 pounds of fuel per hour when it's flying at 125 miles an hour, which is 2 pounds per minute. And again, I've repeated the acceleration to get it off the runway. Once we get to the point where we're going to start the ascent, we're going to go from 7,244 feet to 8,690 feet, going up flying along at a 12 mile per hour horizontal rate of 17.6 feet per second. And that is a distance of 3.2 miles, which is 16,896 feet, divided by 17.6 feet per second is 960 seconds of flying going up. That takes 202 pounds of fuel, because we're using 0.21 pounds of fuel per second doing this, because we're doing drone flying. We're not doing fixed wing flying. So it took us 14 pounds of fuel to get from the airport to the start of the ascent, 202 pounds of fuel to go from 7,244 feet to 8,690 feet, 216 pounds to get to the end of the ascent. So from the airport to the end of the ascent and back is 432 pounds of fuel. Total amount of fuel use is 14 pounds for the safe takeoff, 432 pounds to get there, do the ascent and come back, plus another 14 pounds to land. So it takes 460 pounds of fuel to do one round trip. And my feeling is probably to bring a tanker truck to that place just north of the Flying M Ranch and refill the plane. If we're going to be testing this plane and learning how it works, we might as well figure out how to land it and turn the engines off and refuel it. There's going to be as much need to understand that process as to understand all the rest of it, and landing it in a absolutely unprepared landing place and filling it with fuel, having landed, and then once it's full, starting the motor and flying off. I mean, that's exactly what the military is going to do, so we might as well do that. All right, and so that's your numbers analysis for this. Google Earth is counterintuitive to me, but what I wanted them to do, okay, and so now let me show you another thing. All right, this is the flight from the airport. Oh, okay, over here is the airport at 5,699 feet. So you can see, here's the red arrow over here at the airport. And they're flying along in over pretty much level land. And then they make the turn here and they go across the Flying M Ranch and they put it down here at the end of fixed wing flying at 7,245 feet. And then they're going to fly up. It says end of ascent via drone flying. End of ascent via drone flying. So they're right here, and I'm going to have them fly up this valley. So they can go from 7,248 feet to 87 feet. So they can do a vertical ascent of 1,500 feet without ever being more than 4 or 5 feet off the ground. So that would allow them to do vertical flying, drone flying, in a manner that's safe, because if something went wrong, they're only 4 or 5 feet off the ground and they can just put it down on the ground. So that's what I was thinking. All right, and so we'll get out of that This was pretty flat. I mean, it's 8,000 feet in the, see now this little hand, if you look down here in the right, it shows you the elevation. So the airport is 5,708 feet, 5,800 feet, 6,200 feet, 6,600 feet, 7,100 feet. So when they get here at the place where we pulled all the buses off and the truck and a couple of Humvees, here, I don't know what this is, but hopefully we could get permission to work here at the Pinyon Springs Draw. And now we're going to start flying up this valley because it's going to allow us to obtain vertical flying with the drone. And this is where I get, okay, so that's pretty flat. And then they make their turn here and they go up over this hill. Okay, and you can see, and I apologize in advance, it's just not my strong suit. This is what I'm trying to show you. Okay, so here is on the other side of Flying M Ranch, 7243, 7306, 75, 76, 77, 78, 8,300, 8,700 feet in altitude. And now I'm going to try to demonstrate to you that this seems to me like pretty stable flying, where if anything went wrong, the guys could just put it down on the ground. See, they even have roads here. And we would, I guess, we'd have the military work out arrangements with everybody so they didn't get mad at us. And we're kind of going up this draw here, or whatever this is called. And of course the Humvees could get up there if they had to, if the pilots managed to do something really stupid. Not stupid, the pilots had something happen that they were not anticipating. I suppose I should be kind to the pilots. And you can see we're trying to point them up to the top of the hill here. End of ascent, right there. And it would only be and of course I would have this anticipation that we would be working on the statistics and sending telemetry to the military for them to put it into their AI supercomputers to modify the CPU maybe. So we would tell the guys to just sit here while we upload and download data, and the guys would, they're pilots. They would say, "Hey, well, could we do something like we'll just take off and land and just, get used to how the plane works." As I think of this plane, this is a plane no one has ever seen a plane like this before. And we would say, "Okay, that'd be fine." And what are they going to do? The very first thing they're going to do is fly over here and take a look at the valley. And they would ask for permission to put the plane in the valley. And we would say, no. But can you not see a pilot wanting to land it right there and walk out over here? Now, I will say I'm not a pilot. I don't know what the wind is doing here. This is a great story. But if this is that plane at 55 miles an hour of wind will start to go up in the air. So it might be, if the wind is not happy around in here, they would be truly stupid to park that plane there and get out of it, because they might come back to find their plane is gone. But maybe not. And this land here, this looks pretty flat to me. And I know that they would spend their time saying, "Do you care? Could we fly over the river?" And of course, me from the caring professions would be going, "No, because if you get over this river and have a catastrophic loss of power, what are you going to do?" You know, I can hear the pilots now saying, "Look, we'll put it down right there. And if we have a catastrophic loss of power, let's see here. I can just hear it now. So this from here, 953 feet. It'd be like, this is nothing. Come on. We'll glide it into right there. And we'll taxi it down the road here, turn it around, and when it's time to leave, we'll do this thing that you make us do where we'll fly 6 or 7 feet off of this road. And how long will it be with any pilot before they figure out they switch to fixed wing flying? They've got 5,700 pounds of thrust. They'll pull the nose up and they can come straight up out of this valley with that plane, just like this. Up they would go, and they'd come across here, and we would say, "What are you guys up to there?" And they're saying, "Oh, we're just doing takeoffs and landings like you told us to here at Coffee Pot Hill." And if they have a significant other, they would have them drive up here on 347 and take them down into the river. I don't know if I would approve of that, but this is something this plane can do with no problems. Now, there was one in the Gunnison, Black Canyon of the Gunnison National Park. I think it's right around in here. My guess is they're not going to let a military unit have a tanker truck full of fuel going around in their national park. But I think everything I've shown you here, Coffee Pot Hill and Poverty Mesa, they are not a national forest. And there was one other place that I found, and I'm going to have to find it again. And of course, they're pilots, and they would say, "This is boring. We did this. We went up this little place. We landed here. We went back. You're not letting us into the river. We have noticed over here near Crestone, we can get up to 13,000 feet. And so could we go over there? Could we go over there, please?" And again, you have to remember, while it's a couple of hours for us in the trucks, from Montrose Regional Airport, for them to fly over there is 129 miles. So while we're messing around for 3 hours, the pilots would just be sitting there waiting. And so we'll go over there and look at that one. So this would be an in the air flying for fixed wing flying. They would be doing fixed wing flying stuff. And then they would put it back into drone flying mode. Of course, Pueblo is right over here. It's only a matter of time before those pilots would say, "Huh, I wonder why we're waiting for the buses. In 22 minutes, we could go over here to Pueblo and swing back." Who would know? Because Pueblo is 67 miles, but maybe the pilots won't do that. Okay, so, and again, here are roads, Highway 17. This is a little bit Grand Sand Dunes National Park, but I think we're not on it. And this looks like a road here where I think that's a road, yeah, where we could drive in the buses. And the reason that I picked this one is Crestone, mighty Crestone. I think we could get out here. This is at 8,100 feet. And this is at 12,000 feet. So this is a 4,000 foot vertical ascent. But again, and I apologize that I just don't fly Google Earth very well. But you can see there's a trail here. So the Humvees could go there if the pilots manage to completely screw everything up. Hopefully they won't. But I don't know how tall these trees are. I think that plane could land in this without tearing itself to pieces. And I tried to put a path here again, zigging and zagging up the mountainside for the purpose of doing a vertical ascent. So they would be doing all of this under drone flying. They would not be doing it under fixed wing flying. They'd be doing it under drone flying, where they're getting some ascent. They're getting additional height of the drone with drone flying in a way where if something went bad wrong, they could just land it. And they could slip along here. Sorry, I got lost. Okay, so again, they're flying along this valley floor, moving the plane along. It's just not clear to me. You know, they wouldn't be able to land there, so they would have a little piece of land here where they would be in trouble if they got in trouble, but hopefully they're not going to get in trouble there. And up here, they would have this flat area where they could settle down and be at the at what is our altitude, 11,984 feet. And again, they would, I'm sure, we would tell them they'd have to sit while we mess around and get the telemetry and connection to the main governmental computer. And they would once again be saying, can we practice some takeoffs and landings? And what I think they would do, because they're pilots, is, and this is all doable with this plane, which most planes can't do. They would put it down here, tell us they're there, they would turn it around, and by fixed wing flying, they would come back to here, and then they'd turn it back into drone flying, turn it around, get back into fixed wing flying, and come roaring up here and lift the nose up and go up this. Now this is, what is this height here? Right in here, this is where they're supposed to be, 12,000 feet, and this is 30, so they'd go right up in the air by 1,000 feet, and this is where I put the other landing point, and they would put their plane right here and look out over there. They would call this the crow's nest. And whether they would, I don't know, they can't bring their significant other with them, but you got to admit that's pretty cool. And they would say, well, we're doing takeoffs and landings, could we, do you care if we go zooming down this other valley over here? I mean, we'll be safe because we've got a valley, and we'll go zipping down here like this and come out, and they would come all the way down to here, and they'd peek out, and they would look at us over there and hope we didn't notice where they were. And then they would turn the drone around. And again, I'm embarrassing myself with Google Earth. But they're right here. They peeked out. They lifted it up in the air a few hundred feet. What is this? 9,000 feet. What is this? 8,500 feet. So they went 500 feet in the air, and they looked at us to see if we were looking for them, and then they put it back down, and then they're pilots, and they've got this hot rod where they can put that thing in fixed wing flying and put full power on it and zip up this valley and head for the crow's nest up here. Again, it's not what I do for a living, so they would have to remember how they did this. But they would come up the valley, swing around the crow's nest, which is, oh, right here. Here's the crow's nest, right there. And I think that would become a mark of distinction among the pilots of who landed on the crow's nest and who didn't. And then they would, again, I'm not good with Google Earth, but they would, all of what I'm doing with this, they can do with that airplane. That's what's so crazy. And then the other team down below would say, "You guys, where are you guys?" And they go, "Uh-oh." And they lift it straight up, point the nose down, put it in fixed wing flying. I mean, we're supposed to be testing drone flying, and they'd go barreling down this valley here. And somewhere around in here, you know, they would switch off fixed wing flying and switch it back to drone flying, and then they would arrive and tell us, well, you know, we had a little trouble with the takeoff. I just don't know that you can give military pilots, this plane can go from 0 to 60 miles an hour in 3 seconds. That's 32 feet per second is the acceleration. Now, they I'm sure would ask and be sure that the plane can take that kind of misbehavior. And so now we're back to here, and so, you know, we would have done should not have. They can do it with fixed wing flying while we're messing around with the telemetry, but the formal and official testing is to get 2,000 or 3,000 feet of vertical flight with drone flying without the drone ever being more than 10 or 12 feet off the ground, and maybe doing 30 miles an hour, so that if we had a catastrophic loss of power, they just glided on down and landed. Or maybe 4 or 5 feet off the ground, and instead of 300 feet off the ground. And the only thing I can think is it may be that real actual pilots would just laugh and say, you don't test an experimental plane by flying it 4 feet off the ground. That's crazy. I really just don't know. But I wanted you to see what this plane can do. And there's no other plane can do this. They don't have a plane that doesn't exist. And the final thing I wanted to show you. All right, I'm very intrigued at the idea of seeing if they can be a control panel for these drones where it's the same control panel for all the drones. And this is something, this whole setup could be sent to the different bases as a simulator for them to practice with it. And this is what I want to have inside the drone. Now, there's going to be a place here where they have a little bit of trouble seeing because these screens are in the way, but I think it's worth having this. And I'm going to do an entire YouTube video on this standardized control panel. The interesting thing, in the old days of flying, you started the engine and flew the plane. And as it matured, they had a autopilot, and if you wanted to mess around with the autopilot, you could, but it wasn't necessary. I think with these drones are flying themselves. You're not flying it. So I think it's all going to flip, where you take off and fly it and spend most of your time flying it with the autopilot, and if you want to mess around with the joystick, you can, but you don't have to. And this is because I don't think we should try to have a system where military pilots with 4 or 5 years of training are the only people that can fly this drone. I want the drone to use its autonomy capabilities to let just regular people fly it, because all you're doing is telling it what you want it to do, and it does it. It keeps you out of trouble. All right, so I'm going to make the this guy here disappear, because it makes it easier to see. And this is the main control panel, and I'm going to go over it in much more detail. But what I got to thinking, what if you had to just fly this drone, what would you need to do to make it fly? And one would be the heading, the altitude, and the airspeed. And this is what it really is. And this is what you have requested by turning this knob. And when you turn this knob, the CPU will then make the drone go do it. And there's some features of how fast it changes, and you can put limits in there. You can put in a required, these are LED screens. So it will display information here when it's on. These are momentary toggles. When you push it over here to enable it, and you let go, it comes back to there. If you want to unenable it, you push it over here. It will allow you to set it. And then and the reason for doing momentary toggles is so that when the drone is turned off and turned back on again, everything's ready. None of the toggles, they're all back to their neutral position. And with the altitude, I like the symmetry of this, but I realize with altitude, you're going to have to be careful to be above the ground or above sea level, because I would put a radar altimeter in this drone, since they're flying 4, 5, 7 feet off the ground and doing vertical descents. They need to be given information about above the ground. And and there's a lot of displays. You know, this is fuel remaining, runtime, range available, total fuel available. These are little screens, and you can transfer the little screen over to the big screen if you wanted to, or if you're a pilot and you just the way you trained, if you want to put your artificial horizon there, you can put that there. But what I wanted to show you, and I just have to smile, these rotors have that tilt rotor capability that I think is simple and strong, and you're not going to break it, and I don't think it's going to not work. And if you set the altitude for like 9 feet, then the CPU will run the engines to give you enough power to keep you at 9 feet. So you can go over here and mess around with the rotors, and if you need more power, it'll give you more power. And some of the switches that you have, you can enable the joystick or disable it, and you can convert it to fixed wing flying or not. And this is the one I think the real pilots are going to find immediately, and that is to turn off automatic control of the tilt and take control of it themselves. And this is the front left rotor, front right rotor. That's the RPMs. These are LED screens that will display what the real RPM is. So they can individually adjust them. This one would control the front two. And this one would control all of them. So I could see a pilot getting that drone out there on the runway, taking this and turning all the rotors to horizontal flight. Well, that's real interesting, because that back rotor might hit the ground. So they would have to leave the rotors at vertical thrust, put themselves 6 or 8 feet in the air, and then start easing the rotors over to horizontal and watch their airspeed. And as soon as their airspeed got to 30 miles an hour, they would have 1,200 pounds of lift, and they can start lifting the nose up, and then they can just ease these things all the way down to full horizontal, and they would take their hands over here to the airspeed and crank it up to 150 miles an hour. And what happened is the CPU would take all the power. Now, I think the CPU should be set up so it doesn't ever use emergency power from the jet. And so they would spend maybe 8 or 12 seconds getting to 30 miles an hour. If they then tilted the rotors all the way down and floored it, they would be up at 60 miles an hour in 3 seconds. And what they would do, all right, we would want them to be going up the valley in non-fixed wing flying. That's what we're trying to look at. And when we told them they could do some takeoffs and landings, they would put it on non-fixed wing flying. They would put the rotors to manual control. They would go over here to the altitude that would be set at 0, because that's why they're on the ground. They'd run the altitude to 10 or 12 feet. They'd start pushing the airspeed up, and they would switch the rotors to a horizontal thrust and push themselves up to flying. And that's when they would fly up over the hill. And when they got over to the top of the hill and were looking down at the crow's nest perch, they would flip off fixed wing flying and go back to drone flying. And they wouldn't have to be so worried about it, because the CPU will look at their altitude above the ground and give them enough power that they don't hit the ground. And then if they wanted to, they would be facing whatever direction that is. But all they have to do is turn the heading, and it would turn them around, and they could lower it down onto that crow's nest perch there. Then they could run up their altitude again and run up their airspeed and flip over back to fixed wing flying and go zooming off down that other valley that I was telling you about. This is all stuff that they could do, like that river landing. They could fly out over the river with fixed wing flying, flip it back to non-fixed wing flying, and start backing down their airspeed and backing down their altitude, and they would be easing themselves down into the river valley. And they would point themselves towards that, giving themselves a heading to point themselves towards that road there on the side of the river, if they ever got permission. I just can't see giving them permission to do that. Oh, and the other thing, I created a joystick. It's very interesting with the joystick if you're doing drone flying versus fixed wing flying. And I put the joystick in here, I put a hand on it so you can see how it works. And what I'll do is I'll make the hand go away. And this is the joystick. Okay, and remember, I made up this definition that I created myself. So drone flying is when the device is being held up in the air by its propellers. And fixed wing flying is when it's being held up in the air by its wings. So if you're in drone flying, okay, this control gives you your max airspeed. So if you're doing drone flying and you push the joystick all the way forward, the drone will fly level all the way forward up to this airspeed that you put here. So if you put this at 8 feet per second and push this as far forward as it would go, the drone would fly forward at 8 feet per second. If you pushed it halfway forward, it would fly forward at 4 feet per second. If you pulled it all the way back, the drone would fly backwards at 8 feet per second. It wouldn't change its heading, it would just fly backwards. If you push the stick to the left, the drone would fly to the left up to 8 feet per second and to the right. And if you wanted the drone to change its heading, that's what these buttons are. Your thumb will fit here. So if you push with your thumb, if you push this button, this is the heading here. If you push this button, the heading of the drone will start to change. And if you let go of this button, whatever rate of change of heading you're on will just keep happening until you push this button. And that says, don't change the heading anymore. And these two buttons change the altitude or the vertical velocity. So if you push this button, the drone gets a vertical velocity, and it will keep that vertical velocity until you hit this button, and then it will stop. And these two controls are the rudder. With drone flying, if you push this one, the drone will turn to the right. And if you let go of this, it just stays there. So if you pushed this one and got the drone to turn to the right, if you wanted to turn back to the left, this is to the left. So if you wanted it to go back to the right, you'd have to push this one down. And if you push this one down, it would come back. Well, as soon as you let go of this, it would stop. And if you didn't want to really, so this, I think, would change it by maybe 5 or 10 or 12 degrees. So that's what happens with drone flying. With fixed wing flying, this just becomes a joystick. You pull back on the joystick, the nose goes up. You push forward on the nose goes down. This is a roll to the left, a roll to the right, and this controls your yaw. And so this is the joystick that I created, that is a joystick controlling how the plane is flying. And remember what this joystick is doing. Whatever value you create by putting your hands on that joystick, okay, whatever you do to change, say, let's say you change the heading. Over here on the heading control, the heading would change. And if you took your hands off of the joystick and changed the heading over here, the heading would change. So these are slave units that are reflecting what you're doing with the joystick. And I also put in here a ball mouse and a keyboard. And these, I'll go over these. These are kind of a multi-purpose screen. And what this screen is showing depends upon what the pilot asks it to show. It can show navigation or engine or weapons or whatever he asks it to show. And this is the main control panel. And this is where I think those pilots are going to get in here, and they're going to go right to there and turn off tilt control. Because if you leave tilt control on, then if you ask for fixed wing flying, it will bring you up to 65 miles an hour horizontal flight with the thrust brought to horizontal. And you won't do it. The CPU will do it. And like I said, I just thought you might enjoy that. I'm going to do a whole lecture on it. And so now we're finally at the point where we're from, and I still think that those pilots, I guess if it's a flying program, we should always end with flying near Mayher. You have to wonder what this is, but this is the third place to put the drone for a picture. Remember that picture that I started out with? That's where that was. We would be here in the Humvees yelling at the pilots, "What are you doing over there?" And they would be like, had to put it down for a second. It's not a big deal. Everything's fine. And they'd be sitting here with their significant other eating lunch. Like, you told us to practice landing, so that's what we did. But that's where that one picture came from. And the other picture, and this was the mild and gentle test one, where it went up about 1,000 feet. And the other one is I always get a little turned around here. Oh, there it is, right there. This is the one where you get to 13,000 feet. And that picture was taken on this little flat place. So here, over here, here's where they came up the valley, being good people, listening to us, not being pilots, running it like they're supposed to. And when we told them they had some free time while we messed around with the telemetry, they zipped it up to here and landed on this flat spot right there. So there you go. I think you should, before you get into numbers, why not do a little bit of flying?